Hello again, and welcome to our second lecture on techniques of integration. Last time we reviewed our fundamental formulas for antiderivatives, and today we'll look at two techniques that I think you'll find quite interesting. The first is integration by parts, and it's based on the product rule for derivatives, and it's a very powerful method for integrating products of functions. And then in the second half of the lecture, we'll look at integrals involving trigonometric functions. And again, I think you'll see some interesting results. I'll also try to intersperse some applications, some volumes and things as we go through today's lecture. As I've said many times, integration is a big topic in calculus courses. It's not so big on the AB advanced placement exam, but it is a big topic on the BC examination. And of course, in college calculus courses, integration plays a major role in both first semester and second semester calculus. So let's first look at the technique called integration by parts. It's based on the product rule. And this derivation may look a little complicated notationally, but after I derive it, I'm going to do an example that'll make everything, I think, crystal clear. So remember the product rule. I'm going to deal with two functions, and everybody seems to call them u and v in this business. So we're going to calculate the derivative of u times v, and of course that's the first times the derivative of the second plus the second times the derivative of the first. In other words, if I want to use the prime notation, uv prime is u times v prime plus v times u prime. That means that if I take that equation and integrate both sides of it, I can get a new equation, and the left-hand side of the equation is just u times v. Remember, integration and differentiation are basically inverse operations. So if I integrate that derivative, uv prime, I'll end up with just uv. And the right-hand side is the integral of u times v prime, and then plus v times u prime. And now I'm going to start using that differential notation. So I'm going to write uv prime dx as u dv. This is the way they tend to write it in all the textbooks. Think of it this way. V prime is dv dx. So in a sense, the dx's cancel each other, and you're left just with dv. The same thing happens with that second integral, the integral of v times u prime dx. Think of u as being du dx, cancel the dx's, and you're left with the integral of v du. So we're going to use this differential notation that we touched upon in an earlier lecture. So far a lot of work. We finally arrive at our formula. What we do is, in the previous equation, we have uv equal to a sum of two integrals. Well, take the first one and leave it on the left-hand side, the integral of u dv, and then the right-hand side is uv minus the other integral, v du. So that's the formula for integration by parts. The integral of u dv is uv minus v du. And you might be saying to yourself, well, so what? How can this help me? What's going on? Why does this work? Why is it important? In the next example, we'll see the following happen. We'll be given an integral that is hard. We'll apply this technique, and it'll give rise to another integral, the one on the right, v du. And that one will be easy. It's kind of a miracle. So let's do an example, and I think you'll see how this works. Let's try to find the antiderivative of x e to the x. Can you think of a function whose derivative is x e to the x? I hope not. It's not clear how to even proceed with this problem. Well, we'll try integration by parts. And the idea is to take the integrand, x e to the x, along with the dx part, and part of it becomes the u, and part of it becomes dv. Because remember, in the formula, the left-hand side was the integral of u dv. So I have to make this thing look like the left-hand side. And you have to guess. I'm going to guess u to be x and dv to be everything else. So dv is e to the x dx. Good. Once you've selected your u, you then calculate du, which is the derivative. So du here is the derivative of x, which is just dx. The differential of x is dx. So I differentiate the u part, and the dv part I integrate to find v. And the antiderivative of e to the x is, of course, itself. So v equals e to the x. So those are the substitutions. Identify u, identify dv, differentiate u, integrate dv, and now plug it into the formula. And a miracle is going to occur. All right, the left-hand side is the integral of u dv, and that is x e to the x dx. It equals u times v. Okay, u is x, and v is e to the x. So it's x e to the x. Minus an integral. The integral is v du. Who's v? V is e to the x. And what's du? It's just equal to dx. So my new integral on the right-hand side is the integral of e to the x dx. Look what happened here. We took the original problem that was, whoa, really hard, and we've converted it using integration by parts to x e to the x minus another different integral. Is that new integral easy? Ha! The antiderivative of e to the x is itself. So we have the answer. The answer is x e to the x minus e to the x plus c. Wow. You see what happened? It's kind of amazing. And of course, you can check your answer. If you differentiate that answer, if you differentiate x e to the x minus e to the x plus a constant, you will come up with x e to the x. I invite you to do that. Great. So let me step back now and talk about integration by parts. I like to think of it as magic almost. You start with an integral that you don't know what to do with. You do these conversions, the u and the dv, and boom, out pops a new integral that hopefully is easier. That's the goal. Generally speaking, you know, who's going to be the u and who's going to be the dv? It takes some practice, and sometimes you guess incorrectly. But generally, think of dv as being something that you can integrate, because you're going to have to integrate dv. And it's nice to pick a u that you can differentiate and have it be simpler than what you started with, because you want things to improve. You want the new integral to be easier than the one you started with. You don't need to worry about constants of integration here until the very end when you add the constant of integration. And needless to say, practice makes perfect here. Rewrite the lecture notes and practice doing some of these problems. The workbook has a lot you can practice with. Let's try another one and see if we're comfortable with integration by parts. Here is the function whose antiderivative we desire. It's x squared log x. Who should be u? And then once you've picked u, the rest of it is dv. Well, let me make a bad guess. Suppose I said let dv be log x dx. Just think of that for a moment. I would then have to integrate log x to get v. And I don't know the antiderivative of log x yet. Trust me, we'll know in a few minutes, but that would not be a good method, would it? Because I can't integrate log x, so I have to do something else. How about if I let the dv be x squared dx? That I can integrate. It would be x cubed over 3. Well, then what would u be? U'd be log x. And I have to differentiate the u, and that's easy. The derivative of log x is 1 over x. So that's a better choice of u and dv. So let's do it now. Let u be log x, and dv is everybody else. So it's x squared dx. Those are my choices. Once you've made those choices, you just plow away. You just start churning the machine. The derivative of u is 1 over x dx. And the antiderivative of x squared is x cubed over 3. So my v is x cubed over 3, and my du is 1 over x dx. Good. Plug them into the formula. Here we go. The original problem, x squared log x dx, becomes u times v minus the integral of v du, and we're hoping that new integral is easier to solve. All right, what's u times v? That part is log x times x cubed over 3. That's the u times the v, minus the integral of v du. What's v? V is x cubed over 3. And what's du? It's 1 over x dx. Let's simplify that. We get x cubed over 3 log x as the first term. That part's already done in a sense. We don't have to worry about that one. And then we have our integral, which is, well, if you factor out the 1/3, and then x cubed over x is x squared, so it's minus 1/3 x squared, well, minus 1/3 the integral of x squared. And then you pause and say, hey, can I do this new integral? Have things improved? And you smile and say, yes. The antiderivative of x squared is x cubed over 3. So the final answer is x cubed over 3 log x minus x cubed over 9. The 9 is from the 1/3 out front, and the x squared, the x cubed over 3. So that's the final answer, plus an arbitrary constant. Amazing, isn't it? I really think it's a fun technique. You have to be clever in your guesses, and then, amazing things happen. A problem that looked really difficult turns into something you can do. I mentioned that we didn't know the antiderivative of log x, kind of a blank spot in our knowledge so far. We know the derivative of the logarithm function. It's 1 over x. What's the antiderivative? Well, I'll show you now. And I'll word it as a differential equation. Let's solve the differential equation y prime equals log x. Basically, what we have to do is integrate log x to get the solution. Okay. Well, this is kind of weird. We want to integrate log x dx. Who is u and who's going to be dv? Well, there aren't many choices here, are there? U is going to be log x. That's about all I can choose. And dv is then just the dx, all by itself. So here are the choices. U is log x, dv is dx. Once you've made those choices, you have nothing else to worry about. It just goes. The derivative of u is 1 over x, so du is 1 over x dx, and the antiderivative of dx is x. Okay, so those are our characters. Let's put it together. The integral of log x dx equals u times v. U is log x, v is x, so it's log x times x minus a new integral, the integral of v du. And who is who here? V is x, and du is 1 over x dx. So we have x log x minus, and that integral is the integral of 1, so it's x. The final answer is the antiderivative of log x is x log x minus x plus a constant. There's your antiderivative of log x. Not so simple. You can check it, of course, by differentiating the answer, and you will end up with log x. I'm always amazed when I teach freshman calculus sometimes, and most of my students come into the class, if they took high school calculus, with this formula memorized. They just, for some reason, this is a formula that students just seem to know. I don't recommend memorizing it because, gosh, just not enough room in my brain to memorize all these formulas. But I'm always amazed with the young students that seem to know this formula by heart, the antiderivative of log x. It's not a very simple formula, but there it is. Good. Let's now do an application. I want to go back and remember some of the skills we've developed in this course. We've talked about areas and volumes. How about if we take a a region in the xy plane and find its area, and then we'll rotate it about the x-axis and then rotate it about the y-axis and find the volumes corresponding. So let's take log x, the x-axis, and the line, the vertical line, x equals e. It's the logarithm function which crosses at 1 and goes up to e. And I want the area under that curve, and then I'm going to rotate it about the x-axis, and then I'm going to rotate it about the y-axis. Good. So how about the area under that curve? Well, that would be the integral of log x between 1 and e. Well, we know the antiderivative now of log x. We just derived it. So the area under that curve between 1 and e is the definite integral from 1 to e of log x dx, which turns out to be x log x minus x, and then you plug in the endpoints 1 and e. Remember, you don't need the constant of integration. You just need an antiderivative, and that's an antiderivative. And if you plug in e, you get e log e, which is just e, because log of e is 1, and then minus e, and then you plug in 1. 1 log 1 is 0, and then minus a minus 1. So the final answer is 1. Kind of a curious answer, that the area under that little logarithm arch is 1 square unit. Again, kind of strange to me, given that the logarithm function is fairly complicated, and yet the area under it is so simple. Now let's rotate it about the x-axis. You can sort of see a little picture here. I've rotated it about the x-axis. What's the resulting volume? Remember how disks work. You slice it up into pancakes or disks. They start at 1, they end at e, and the volume of a little disk is pi r squared, that's the area of the circle, times dx, which is the width of the disk. So our formula becomes the integral from 1 to e of pi times the radius squared, and the radius is log x. So our integral is pi, integral from 1 to e, log x squared. And we have a problem. What's the integral of log x squared? Quantity squared. Let's try integration by parts. That's our new skill for the day. So we let u be log of x squared. du is then forced upon us to be the derivative, so it's 2 log x times the inside derivative 1 over x. dv is dx, that's all that's left over, so v integrates to be x. So now we do integration by parts. The integral equals u times v, u is log of x squared, and v is x, minus the integral of v du. V is x, and du is 2 log x over x. Good. Kind of complicated. This kind of simplifies a little bit. The first part is still x times log x squared, and then the second part is minus 2. The 2 comes flying out. The x's cancel, and you're left with the integral of log x dx. So we've reduced the problem of integrating log x squared to the problem of integrating log x. In a sense, we'll now do integration by parts again to get the answer for log x, but we just did that a few seconds ago. So I know the antiderivative of log x. Let's plug that in. And we have x log x squared minus, and now it's 2 times the antiderivative of log x, which is x log x minus x, plus an arbitrary constant. Now, all of that work was just to find the antiderivative of log x squared, because that's the radius squared. Now we have to do the volume. It's pi times the radius squared. So it's pi integral from 1 to e log of x squared, and now I know the antiderivative of that baby. So it's pi times the quantity x log x squared minus 2x log x minus x. Wow. And I have to plug in 1 and e into that. It takes a little bit of time. You plug in E, you get E minus 2 times the quantity E minus E. And then you plug in 1 and you get a minus 2. That compactifies to pi times E minus 2. Okay, that was some hard arithmetic at the end, and it was integration by parts actually twice, reducing log x squared to log x, and then finally the final answer. Let's now rotate it about the y-axis. Well, now we'll use shells. Remember the shell method. The volume of this is going to be the summation of our shells, and a typical shell has a width of delta x, it has a height of the function value, log x, and then it's 2 pi times the radius, and the radius is x. So here's our formula. It's the integral from 1 to e, 2 pi times the radius, so 2 pi x, times the height, which is log x, and the width was dx. Now, I'm tired of doing integration by parts, so let's not do this one out, but you'll get the final answer of pi times e squared plus 1 over 2. You might ask yourself, who would be u in this problem? And I think probably the best guess would be u to be log x. You can see the workbook for details on this problem. Good. Let's spend a little bit of time now on a different class of integrals that occurs a lot in practice. And these are functions that are formed from sines and cosines, tangents and secants, combinations of trig functions. And let me begin with some simple examples to sort of show you what's going on here. Suppose you had to integrate sine to the 5th times cosine. Okay, sine to the 5th times cosine. What would you say? Well, if I let u be sine x, its derivative is cosine, isn't it? And it's sitting right there. So this would be u to the 6th over 6, or sine to the 6th x over 6 plus a constant. Check that answer. Watch what happens when you differentiate sine to the 6th power x over 6. You get 6 times sine to the 5th, and the 6 is canceled, times the inside derivative cosine. So we got it right. So if you have a single cosine and a bunch of sines, things are going to be okay. Well, here's a little more complicated, but this is also going to be okay. Suppose you have sine to the 4th x times cosine cubed x. Looks difficult, but watch this little trick. I think you'll enjoy it. Take the function and split off one of the cosines. Put it over there next to the dx. And now take the other cosines. Now it's cosine squared. That's left over from the cosine cubed. And turn that into 1 minus sine squared by your fundamental trigonometric identity. So our problem becomes sine to the 4th x, cosine squared x, cosine x. I now convert cosine squared to 1 minus sine squared x, and then multiply that out. And you have the integral of sine to the 4th x minus sine to the 6th x, all multiplied by cosine. Now, is that difficult? Well, let u be sine x. Its derivative is cosine, and it's right there. And the same with sine to the 6th. So I think you see that the final answer is sine to the 5th x over 5 minus sine to the 7th x over 7 plus a constant. What can we glean from all of these, from these two examples? If you have sine or cosine to an odd power, the problem will be easy when you're confronted with a product of sines and cosines. Because if either one's an odd power, you steal one of them and move it over to the right, and then you have an even power, and you can convert that to the other trig function. If they're both to even powers, it's tough. It can be hard. And we won't dwell on that thing. Now, the same thing happens, by the way, with combinations of tangent and secant. Let me show you an example of that, and you'll see the same kind of mechanism working here. Let's find the antiderivative of secant to the fourth times tangent cubed. Here we go. I remember that the derivative of tangent is secant squared. So what I'm going to do is take two of the secants squared, and move it over to the right. And I'm left with secant squared. So my problem becomes secant squared, tangent cubed, secant squared. And now convert that secant squared on the left to 1 plus tangent squared by the trig identity. Tangent squared plus 1 is secant squared. So now I have 1 plus tangent squared times tangent cubed, all multiplied by secant squared dx. Well, combine all the tangents together. You have tangent cubed x plus tangent to the fifth x, all times secant squared. Let u be tangent. The derivative of tangent is secant squared, and it's sitting right in front of us. So the antiderivative is tangent to the fourth over 4 plus tangent to the sixth over 6 plus a constant. Good. It turns out with these combinations of secants and tangents that you also can do it another way. We could also pull out secant tangent to the right and then leave everybody else on the left. So let's do that, and you'll see an interesting occurrence. So now I take one of the secants and I take one of the tangents and move it over next to dx. What am I left with? I'm left with secant cubed and tangent squared times secant tangent. Now, why did I do that? Well, now I'm going to convert the tangent squared to secants. And what's the derivative of secant? Secant tangent, which is sitting over there on the right. So tangent squared is secant squared minus 1 by the same trigonometric identity. So our problem becomes secant cubed times the quantity secant squared minus 1 times secant tangent. Good. Multiply that out. You get secant to the fifth minus secant cubed times the secant tangent. Let u be secant. What's the derivative? Secant tangent. It's standing right there. So the final answer is secant to the sixth over 6 minus secant to the fourth over 4 plus a constant. So we just did the same problem 2 times, and we seemingly got different answers. One of them was involving tangents, and the other one was involving secants. It turns out they're equivalent to each other. Good. And generally speaking, if you have tangent to an even power or secant to an odd power, then you cannot do these tricks. The easy cases are tangent to an odd or secant to an even. In that case, the problem is easy. But if tangent is even and at the same time secant is odd, you're bad news. It's really hard. For instance, the integral of secant, that's an odd power, power of 1. That's very hard. It's logarithm secant plus tangent. The integral of secant cubed is really hard. So don't try to do it. Good. I mentioned a while ago that we had a problem involving the integral of sine squared x dx. Let me briefly show you how you would integrate an even power of sine, like the square. You use a half-angle formula from trigonometry. Sine squared is 1 minus cosine 2x over 2. And then that integral is pretty straightforward. It's the integral of 1/2, which turns out to be x over 2, and the integral of cosine 2x over 2, which turns out to be sine 2x over 4. So the final answer is x over 2 minus sine of 2x divided by 4 plus a constant. If you were ever confronted with cosine squared, you would do the same trick, but use the trig identity that cosine squared is 1 plus cosine 2x over 2, and then use substitution. I can't emphasize enough that practice makes perfect here. This is not a spectator sport, so please, do some of the problems in the workbook, and you'll get very good at finding antiderivatives. You've also got to be creative. You've got to sort of make some guesses. And don't forget, you always can check your answers by differentiating. So next time, we're going to turn to another topic that we've alluded to previously, and that's differential equations. We'll spend the final 2 lectures on differential equations. This is a very applied area of mathematics, and it's kind of interesting that differential equations play a very big role in the advanced placement syllabus, yet in freshman calculus at universities, it doesn't play such a big role. The reason being universities have differential equations courses, entire courses after calculus. That said, I think you'll enjoy the next 2 lectures because we'll talk about a broad range of applications of differential equations. Thank you very much, and see you next time.